Imagine this. The universe, everything we know and don't know, might have started from something as tiny as a bubble. Not the kind you blow with gum, but a quantum vacuum bubble, a tiny fluctuation in the fabric of space and time. This isn't science fiction. It's a serious idea that scientists are exploring. If you've ever wondered about the origins of the universe, or if you're just curious about the weird and wonderful world of quantum physics, stick around. We are diving into the mind-bending concept of quantum vacuum bubbles and their potential role in the birth of our universe. It's a journey that might make you see the cosmos in a whole new light. Nario, 8 points. The Nario, 8 points framework offers a unique perspective on quantum vacuum bubbles and their potential role in the universe's origin. It suggests that these bubbles, tiny regions where quantum fluctuations create a vacuum, might have been the seeds of our universe. Think of them as tiny bubbles in a cosmic ocean, each with its own unique properties. When one of these bubbles grows large enough, it could give birth to a new universe. This idea is not just science fiction, it's a serious theoretical possibility explored by physicists. One of the key points of Nario is the concept of eternal inflation. Imagine the universe as a vast, inflating balloon. In some areas, the balloon inflates rapidly, while in others, it inflates more slowly. The rapidly inflating regions are like quantum vacuum bubbles. These bubbles can collide, merge, or even give birth to new bubbles. Each bubble could have its own set of physical laws, different from ours. This idea helps explain why our universe has the specific properties it does. Another crucial aspect is the multiverse theory. Nario suggests that our universe is just one of many, each originating from a different quantum vacuum bubble. This idea is not new, but Nario provides a fresh perspective. It proposes that these bubbles are not just random but follow certain patterns. These patterns could explain the fine-tuning of our universe. For example, why the constants of nature are just right for life to exist. This idea is still speculative, but it's an exciting area of research. Nario also explores the idea of bubble collisions. When two bubbles collide, they can leave behind observable signatures. These signatures could be detected in the cosmic microwave background, the afterglow of the Big Bang. Scientists are actively looking for these signatures. If found, they could provide strong evidence for the quantum vacuum bubble theory. This would be a groundbreaking discovery, changing our understanding of the universe's origin. Lastly, Nario considers the implications for the future of our universe. If quantum vacuum bubbles can give birth to new universes, could our universe do the same? This idea is still purely theoretical, but it's a fascinating possibility. It suggests that the universe is not just expanding and cooling down, but is also potentially creating new universes. This idea challenges our traditional views of the universe's fate. It opens up new avenues for exploration and understanding. Quantum vacuum definition: what empty space truly contains. The notion of empty space is a bit of a trickster. It's not as vacant as one might think. In the realm of quantum physics, even the emptiest space isn't truly empty. This is what scientists refer to as the quantum vacuum. It's a space devoid of matter, but it's far from being a void. Instead, it's a seething, frothing sea of quantum fields and particles that pop in and out of existence. These particles are called virtual particles, and they're not just a theoretical concept. Their effects have been measured and observed in experiments, like the Casimir effect, where two plates placed close together in a vacuum experience a force due to these virtual particles. At the heart of the quantum vacuum are quantum fields. These fields permeate all of space and are responsible for the fundamental forces of nature. For instance, the electromagnetic field is what gives rise to light and governs the behavior of charged particles. Even in a vacuum, these fields have energy and can fluctuate. This is where virtual particles come into play. They are temporary excitations of these fields, appearing and disappearing in a timescale so short that they can't be directly observed. Yet, their existence has measurable consequences. The quantum vacuum isn't just a static backdrop. It's dynamic and can have a significant impact on the universe. For example, it's thought to be the reason behind the slight asymmetry between matter and antimatter in the universe. This asymmetry is what allowed matter to dominate and form the universe we see today. Moreover, the quantum vacuum can influence the behavior of light and particles in ways that can be harnessed in technology. For instance, quantum computers rely on the principles of quantum mechanics, including the behavior of particles in a vacuum. In everyday life, the effects of the quantum vacuum are negligible. It's only at the smaller scales, where quantum mechanics reigns supreme, that these effects become significant. Yet, understanding the quantum vacuum is crucial for advancing our knowledge of the universe. It challenges our intuitions about empty space and forces us to confront the weird and wonderful world of quantum mechanics. From the behavior of particles to the origins of the universe, the quantum vacuum plays a pivotal role. It's a testament to the fact that even the emptiest space is far from empty. Energy fluctuations, how bubbles may spontaneously form. The universe, as vast and empty as it may seem, is never truly empty. Even in the void of space, there's something happening at the smaller scales. This something is called quantum vacuum fluctuations. Think of it like the hum of a refrigerator. It's always there, even if you're not paying attention. These fluctuations are tiny changes in energy that happen spontaneously, even in a perfect vacuum. They're a fundamental part of quantum mechanics, the science that describes the behavior of particles at the smallest levels. Now, these energy fluctuations aren't just random noise. They can have real, observable effects. One of the most fascinating is the spontaneous formation of what scientists call bubbles or vacuum bubbles. These aren't bubbles like you'd see in a glass of soda, but rather, they're tiny regions where the energy fluctuates in a particular way. Sometimes, these fluctuations can be so significant that they create particles out of seemingly nothing. This is a process known as particle-antiparticle annihilation, where energy temporarily converts into matter and then back into energy. The idea of bubbles forming from energy fluctuations might seem far-fetched, but it's a well-accepted concept in quantum physics. It's all about the uncertainty principle, which states that certain pairs of properties, like position and momentum, cannot both be known to arbitrary accuracy. In other words, there's always some uncertainty, some fuzziness, in the universe. This fuzziness allows for these energy fluctuations to happen. It's like the universe is always jittering, always moving, even when it seems still. These bubbles can pop in and out of existence incredibly quickly, often in less than a fraction of a second. But in that brief moment, they can have a significant impact. For instance, they might influence the behavior of other particles or even contribute to the overall energy of the universe. It's a bit like a tiny, temporary disturbance in the fabric of reality. Scientists have even observed these bubbles in the lab. They've seen them affecting the behavior of electrons and other particles, proving that these fluctuations are very real. False vacuum decay, the idea of universe-scale phase transitions. In the realm of theoretical physics, the concept of false vacuum decay is a fascinating one. It suggests that our universe might be in a state of false vacuum, a temporary, higher energy state that could eventually transition to a more stable, lower energy state. This transition is akin to a phase change, like water turning into ice, but on a cosmic scale. The idea is that if a small bubble of the true vacuum forms, it could expand at the speed of light, transforming the entire universe in its wake. This process is driven by quantum fluctuations, tiny, random changes in energy that occur at the smaller scales. Think of it like a pot of water on the stove. If you heat it up, small bubbles of steam start to form at the bottom. These bubbles are like the quantum fluctuations in the false vacuum. If one of these bubbles grows large enough, it can cause the entire pot to boil, changing the state of the water. In the case of the universe, this boiling would be a phase transition to the true vacuum. The implications of false vacuum decay are profound. If our universe is in a false vacuum state, it could mean that it's not as stable as we think. A single quantum fluctuation could trigger a catastrophic event, rewriting the fundamental laws of physics as we know them. However, it's important to note that this is purely speculative. We have no evidence that our universe is in a false vacuum state, and even if it is, the transition could take an incredibly long time to occur. Moreover, false vacuum decay could explain the origin of the universe. Some theories suggest that our universe was born from a bubble of true vacuum expanding into a larger false vacuum. This idea is still a topic of ongoing research and debate. It's a reminder that our understanding of the universe is still evolving, and there's much more to discover. Bubble universe theory, each bubble as a separate cosmos. The bubble universe theory is a fascinating concept in cosmology that suggests our universe might be just one of many universes, each existing as a separate bubble within an expansive multiverse. This idea is rooted in the notion that the universe we observe is just one of countless others, each with its own unique set of physical laws and constants. Think of it like a vast cosmic foam, where each bubble represents a distinct universe, floating in an endless sea of possibilities. This theory is not just a wild speculation. It has some solid theoretical groundings, particularly in the framework of eternal inflation. Eternal inflation posits that the universe underwent a period of rapid expansion right after the Big Bang. This expansion wasn't uniform, though. In some regions, the expansion slowed down, allowing matter and energy to condense and form galaxies, stars, and planets, essentially, the universe we know. In other regions, the expansion continued unabated, giving rise to new bubble universes. Each of these bubbles could have its own unique properties, different from ours. For instance, the laws of physics in one bubble might allow for different types of particles or forces than what we observe in our universe. This diversity is a key aspect of the bubble universe theory. One of the most intriguing implications of this theory is that it offers a potential explanation for the fine-tuning of our universe. The constants and laws of physics in our universe seem remarkably well suited for the existence of life. The bubble universe theory suggests that this fine-tuning might not be so surprising if there are countless other universes with different properties. In this vast multiverse, the conditions in our universe might be one of the few that allow for the existence of life as we know it. This idea is often referred to as the anthropic principle, which states that the universe must be compatible with the existence of observers like us. The bubble universe theory also raises profound questions about the nature of reality and our place in the cosmos. If other universes exist, are they accessible to us? Could we ever communicate with or observe these other bubbles? Current theories suggest that these universes are likely forever beyond our reach, existing in higher dimensions or separated by vast cosmic distances. However, the mere possibility of their existence opens up a wealth of philosophical and scientific questions. It challenges our understanding of what it means to be a universe and invites us to consider the broader context of our existence. Link to Big Bang, rapid inflation from a quantum bubble. The idea of quantum vacuum bubbles is fascinating, and it's even more intriguing when we consider their potential link to the Big Bang. Picture this: the universe as we know it might have started from something as tiny as a quantum bubble. These bubbles are not the soapy kind you see in a bathtub, but rather, they are regions of space where the energy is different from the surrounding area. They can pop in and out of existence due to the strange rules of quantum mechanics. Now, let's talk about rapid inflation. This is the idea that the universe expanded incredibly quickly right after the Big Bang. It's like a balloon being blown up at an astonishing rate. Some scientists think that this rapid inflation could have been triggered by a quantum bubble. The bubble might have contained a different set of physical laws or properties than the space around it. When it expanded, it could have set off a chain reaction that led to the rapid growth of the universe. Think of it like a tiny seed that grows into a massive tree. The seed is the quantum bubble, and the tree is the universe. The bubble's unique properties could have been the catalyst for the rapid expansion. This idea is still theoretical, but it's a compelling one. It suggests that the universe might have started from something incredibly small and simple, and then grown into the complex cosmos we see today. Moreover, this theory helps to explain some of the mysteries of the Big Bang. For instance, why is the universe so uniform on large scales? Why is the temperature of the cosmic microwave background radiation so evenly distributed? A rapidly expanding quantum bubble could have stretched out any irregularities, smoothing them out and making the universe look more uniform. It's like taking a piece of dough and stretching it out so that any small lumps or bumps become tiny and hard to see. This idea is still being explored and tested, but it's one of the many ways scientists are trying to understand the origins of our universe. Mathematical models supporting the idea. Mathematical models have been instrumental in exploring the concept of quantum vacuum bubbles and their potential role in the origin of the universe. These models often rely on principles from quantum field theory and general relativity to describe how fluctuations in the quantum vacuum could lead to the formation of new universes. One key idea is that the quantum vacuum is not entirely empty but filled with fluctuating energy fields. These fluctuations can sometimes create tiny bubbles where the laws of physics might differ from those in our universe. Mathematicians and physicists use equations to simulate these scenarios, showing how such bubbles could expand and potentially give rise to new universes. A significant aspect of these models is the concept of false vacuum decay. In this scenario, the universe is thought to exist in a metastable state, like a ball balanced precariously on a hill. Quantum fluctuations could trigger a phase transition, causing the universe to roll down into a more stable state. This process would create a bubble of true vacuum that expands at the speed of light, potentially leading to the birth of a new universe. Mathematicians have developed complex equations to describe this transition, providing a framework for understanding how such events might occur. These models often involve solving differential equations that describe the behavior of quantum fields under different conditions. Another important mathematical tool is the use of path integrals, which allow physicists to calculate the probability of different quantum events. By integrating over all possible paths that a quantum system can take, mathematicians can determine the likelihood of a vacuum bubble forming and expanding. This approach has been used to study the stability of the quantum vacuum and the conditions under which new universes might emerge. For example, some models suggest that the probability of a vacuum bubble forming is extremely low, but not zero. This means that while such events are rare, they are not impossible. Mathematicians continue to refine these models, incorporating new data and theoretical insights to better understand the nature of quantum vacuum bubbles and their potential role in cosmology. Criticism and alternative explanations from physicists. Quantum vacuum bubbles, while an intriguing concept, have faced significant criticism and alternative explanations from physicists. Many argue that the idea lacks sufficient empirical evidence to support its claims about the universe's origin. The primary issue is that quantum vacuum bubbles are hypothetical constructs, and their existence has not been directly observed. This makes it challenging to validate their role in cosmic events. Critics point out that relying on unobserved phenomena to explain the universe's beginning is speculative at best. They advocate for theories backed by more concrete data. Some physicists propose alternative mechanisms for the universe's origin. One such alternative is the idea of cosmic inflation, which suggests that the universe underwent a rapid expansion shortly after its inception. This theory is supported by observations of the cosmic microwave background radiation, which shows a uniform temperature across the sky. Inflation explains this uniformity by proposing that the universe expanded so quickly that it smoothed out any initial irregularities. Unlike quantum vacuum bubbles, inflation has testable predictions and has been corroborated by various astronomical observations. Another alternative explanation is the ekpyrotic universe model. This theory posits that the universe was created from the collision of two three-dimensional worlds, brands, in a higher dimensional space. The collision would have released an enormous amount of energy, leading to the creation of our universe. Proponents of this model argue that it provides a more straightforward explanation for the universe's origin without relying on the complex mathematics of quantum vacuum bubbles. While this theory is still under development, it offers a compelling alternative that some physicists find more plausible. Critics also highlight the philosophical implications of quantum vacuum bubbles. The idea that our universe could be just one of many in a vast multiverse raises questions about the nature of reality and our place in it. Some physicists argue that these questions are more metaphysical than scientific, and they prefer to focus on theories that can be tested and verified. They contend that until quantum vacuum bubbles can be observed or their effects measured, they remain an interesting but unproven hypothesis. This skepticism drives the search for alternative explanations that are more grounded in observable phenomena. What future experiments may confirm? To explore the concept of quantum vacuum bubbles and their potential role in the origin of the universe, scientists are looking ahead to a range of experiments and observations. These experiments aim to probe the fundamental nature of the vacuum and the conditions that might have given rise to our universe. One promising avenue is the use of particle accelerators, like the Large Hadron Collider, LHC, at CERN. These machines smash particles together at nearly the speed of light, recreating conditions similar to those just after the Big Bang. By doing so, they might produce tiny quantum vacuum bubbles, allowing scientists to study their properties and behavior. Another exciting area of research involves cosmic microwave background, CMB, radiation. This is the afterglow of the Big Bang, and it fills the entire universe. By studying the CMB with increasing precision, scientists hope to find subtle patterns or anomalies that could hint at the presence of quantum vacuum bubbles in the early universe. Advanced telescopes and satellites, like the Planck satellite, have already provided a wealth of data. Future missions could reveal even more detailed information, potentially confirming the existence of these bubbles. In addition to these approaches, scientists are also exploring the use of quantum sensors and other cutting-edge technologies. These tools could detect the faint signals produced by quantum vacuum bubbles, even if they are extremely small and short-lived. For instance, quantum sensors might be able to measure tiny fluctuations in the vacuum energy, providing indirect evidence for the existence of these bubbles. This is a rapidly evolving field, and new technologies are being developed all the time. Moreover, theoretical work plays a crucial role in guiding these experimental efforts. Scientists are constantly refining their models and predictions, using powerful computers to simulate the behavior of quantum vacuum bubbles. These simulations can help identify the most promising experimental paths and interpret the results. As our understanding of quantum mechanics and cosmology continues to grow, so too does our ability to test these fascinating ideas. The quest to confirm the existence of quantum vacuum bubbles is a testament to the power of human curiosity and the relentless pursuit of knowledge. All right, let's wrap this up. So, to sum it all up, we've been exploring these mind-bending quantum vacuum bubbles. They're like tiny, empty spaces that pop in and out of existence, and they might just hold the key to how our universe began. Imagine the universe as a giant bubble, and these quantum vacuum bubbles as little seeds that could grow into something as massive and incredible as what we see today. It's like the universe's own version of a Big Bang starter kit. Now, first know this stuff can be a lot to take in. It's okay if your brain feels a little stretched. Mine does too, and First VE been thinking about this for a while. But that's the beauty of science. It's always pushing the boundaries of what we understand. If you found this as fascinating as First did, make sure to hit that like button and subscribe for more mind-bending explorations into the mysteries of the universe. And if you have any questions or thoughts, drop them in the comments below. First, I'd love to hear what you think. Next time, we are diving into another cosmic mystery. What if First told you that there might be more than one universe out there? That's right, we are talking about the multiverse. So, stay tuned, and let's keep exploring the wonders of the cosmos together. Until then, keep wondering, keep questioning, and keep looking up at the stars. Who knows what we'll discover next? See you in the next video.